Hello, am I audible?
Yes, sir.
Yes,
Yes,
sir,
sir.
you're audible.
Yes, sir.
Okay. So once again, I request you not to use the normal Gmail ID. You should always use the institute email ID. So in this class, this I'll try to complete the introductory part. So we have a few more slides left in the general view of the computing system. So what we discussed about was the memory manager or memory manager module. The issues related to that. We talked about the CPU, some issues related to CPU management, and now in this class we'll be talking about mainly the IO device management, some of the issues related to that, and I'll switch on to the evolution of operating system. But before I get into the IO management module, let me just get into the details of interrupt processing that we started in our last class. So as we found, I just summarize this slide and start with the signal system calls. So interrupts in OS, what we found is operating system is basically a event-driven software or a event-driven program, and it has got multiple modules which will be triggered only if a particular event occurs. And many such events can be defined, and the OS designer's responsibility is to define and find out all possible events related to input output when it is happening due to any error conditions that occurs, and it will define a particular interrupt corresponding to that event. So you can think of that in an operating system there will be a finite set of interrupts, each corresponding to a unique event that might occur while the operating system is running or while the user processes are getting executed. However, apart from hardware interrupts, as we found and discussed extensively in the last class, there may be software interrupts, which may be because of some coding error, some erroneous outcome in some operation, mathematical operation, or it can be that when the user program or user process is willing to access some resources in the system which is not generally authorized. So should make the request via the operating system modules, and he will basically interrupt the operating system and it will make the request. So this also is this is actually done in form of some system calls, which is an interface provided by the operating system. So the user programs can call that system call, and this system call, this execution of the system call is also following the same interrupt processing mechanism. And there are special instructions depending on the hardware or the specific processor, the assembly level instructions, which will be actually used to trigger these software interrupts. And we also talked about the interrupt code. Each and every interrupt will have a unique code, interrupt masking and interrupt action, where corresponding to each interrupt there will be an interrupt service routine, and the link to these service routines will be stored in the interrupt vector table, which accommodates one entry corresponding to all these interrupts that are defined in the system. Okay, and whenever an interrupt occurs, how to check it? At the end of every instruction cycle, the processor will check for interrupts. If it occurs, there will be a context switching. The context of that interrupt processing module will be loaded, and the current process will be saved, and that is how it goes on. So as we mentioned, system calls are also treated as software interrupts. So the same mechanism of interrupt processing is followed whenever we call a system call. So we'll find in some more details how the system calls are working, the internals of every system call. It has got a particular algorithm that it executes. We'll talk about it later on in process management, some of the system calls. So it's a request that a program makes to the kernel through a software interrupt. And say when we write something, like open or read in a high level code, so when the code is compiled, you can think that this gets translated to something like this, and which in turn actually calls a system call. So a simple printf statement requires access to the monitor, as we all know, and the scanf requires access to the keyboard. So when you write the printf, we just call the library that is available, but we can't see the details of what is there in printf. But if you can decode it, you will find that printf actually is calling some system call, is making some system call, which actually calls, interrupts the operating system, say for example like this, and it interrupts the kernel. The kernel knows that it's a access request to the monitor, and it probably will allow, and once it happens, it again comes back, and it comes back here. So even simple printf scanf in the background or in the backend, it makes some system calls, although we don't need to bother about it. We just deal with the high level functions provided. So the system calls are, in some cases, like in this case, it is implicit, but in some cases we can make explicit system calls. Okay, like when we want to create a process, we call for. So you can directly make a system call, or when you call a library, the library can make some calls in turn. And these are the list of, uh, a representative list of system calls. There are many such system calls which is provided in Unix or Linux type operating systems. So now we come to the the discussion of I/O devices. So what we find here is, you see, there is a component called DMA. We have got the device controllers, and we are having the I/O devices. So we talk about each of these, and we find that these DMA is actually having a line connected to the I/O interrupt line of the processor. Okay. So what is a device controller? What is a device driver? Say if this is a device, this is a device means hardware device, input or output. So this device will generally have some hardware component, which we call it as controller. Okay. So the controller is a hardware device. You can think of it as a card or microchip, which may be a part of this device itself, or it may be part of the, say, a motherboard. There is a plug-in hardware which actually is having the device controller. So this is the device controller, which is basically a hardware which interfaces between the device hardware as well as the machine computing system. But this device controller also is not directly communicating with the operating system, because if you look into the computing system is controlled by the operating system. So the OS is not directly communicating with the device controller. Rather, it has got some intermediate software which assists in such communication, and that is called the device driver. Okay. So if you have got this hardware device, it may be a monitor, it may be a printer, it may be keyboard. So we can consider this to be the device controller. This controller is actually the hardware device which interprets the signals that is generated by this device driver. Okay, it will generate raw signals which this can interpret, and it may be that it will interpret in such a way that the buffer that is here, it will activate the buffer, and if it is a read buffer, it will be, the value will be stored here, and it will be forwarded like that. So this control is basically meant for interpreting the signals that the computing system passes on to the device driver, to the actual device. And this device driver is important because this device driver actually knows what kind of signals it need to send to the controller. So it is very much dependent on the controller. If you don't know the controller details, you cannot write the device driver. So this device driver is actually interfacing between the operating system and the device controller. So this is a software and this is a hardware. So this part is a software and this part is a hardware. And that is how you can think of the IO devices are connected to the OS. So every device is having some device controller, and we must install some device driver, as you all know, when we install some new external device. Okay, so this much is enough for us. And before we go to the evolution, there's one more point left: the various types of IO mode, various modes or modes of IO transfer. So IO transfer means, so the CPU wants to uh, read something from some input device, or CPU wants to send something to the output device, read or write operations. So there can be three possible ways how the CPU can execute the read write operation with respect to a IO device. Okay, so there are three terminologies: programmed IO, interrupt driven IO, and direct memory access. And these are probably taught in microprocessor course or in your architecture course. I'll just review the basic concepts, because while referring to the process management, we'll find that sometimes we'll be using a particular type or mode which is more advantageous over the other. So what is programmed IO? We can consider a very simple example. Say for example, when we teach say a small child who is just learning, say, how to add, how to subtract. So he's in say class 1 or something like that. So in that case, if I want to assign say 5 sums to my son, we say for example in class 1. So what I need to do, I assign the sum, but he is so reluctant, and in doing so, so I have to keep monitoring that whether he has done it or not. So the idea is, while he's trying to do that, complete that sum, I have to continuously monitor whether he has done it or not done it or not. So once he is done, I have to check it, and then only I can give the next sum. Again, I have to keep monitoring like that. So to uh, get him done with 5 sums, I have to probably be busy for 15 minutes, and I can't do any other work during that period of time. Now when he grows up, like when he is in say class 7 6 or 7, he has grown up, so he can take a bit of responsibility, and he's more now responsible. So now in that case, what we do, so I give him a sum, and he's a bit responsible, so he does it of his own. And once he completes, he then interrupts me that, okay, I am done, so can you check it and give me the next sum. So earlier what I did, once I give the sum, even if my son completed, he didn't interrupt me that I am done. He just sits idle and playing some with something else. So I have to monitor it repeatedly. I have to poll that status. But in the second case, it's similar to the interrupt driven. The first case is programmed IO. In the interrupt driven, I assign the sum, and I expect, and my son will complete the sum, and he will interrupt me that I am done. I'll check it. I'll give the next sum. So while he's solving the problem, I can be busy with some other activities. Say in this case, myself is a CPU, and my son is the IO device kind of thing, and doing the sum is something equivalent to transferring data uh, from the input to output device. Okay, and each and every sum is just like writing a block, and the task is to write multiple blocks. Okay, so as we can see that interrupt driven IO, or the second mode, is a much better option, because the CPU or I can be busy with my own activities at least for some time. But the best option is, but still it is not relieving the CPU from monitoring. So the best option is something like this, so which I can probably adopt when my son is in class 9 or 10. Okay, so he's in class 8. So now he's even more responsible. So if I say that, okay, I have set you 5 sums, I have assigned you 5 sums. So what he does, he executes each and every sum, checks the answer if he is correct or not, and he completes all the sums. And after completing all the bunch of 5 sums, he interrupts me that I am done. Okay, and then I can cross check it and I can assign some other tasks. So now here the basic difference is I don't have to be busy in between 2 sums also. Okay, so that is how I am completely relieved. So DMA is something like that. So here the CPU issues a command to the DMA module in terms of IO transfer, and the DMA completes the entire transfer of all the blocks. So the thing is, the CPU is completely relieved when this DMA transfer is going on, a block getting transferred from input or output devices. And once it is done completely, like the DMA reads from this, say maybe input device, all the 5 blocks, and then copies it to the RAM, and it says that, so it sets an interrupt pin that I am done, and then CPU then continues with execution. So in this case, the CPU can completely occupy itself with other activities like processing rather than being engaged in IO. So if we have the DMA support, the hardware support in our system, we can expect that the CPU and the CPU execution and the IO can be interleaved. Interleaving means they can go in parallel. Okay, so definitely if you can think of that, the system can accommodate multiple processes. If there is a single process, so single process cannot do CPU execution as well as IO simultaneously. That is not possible. But if you have got multiple processes accommodated in the system, as we'll see in a typical multi-programming system, we can have multiple programs or processes simultaneously active in the system. Then it might happen that if you have got a single CPU, so one process is getting the CPU getting executed, and the others are busy in input output without any direct intervention of the CPU. So the CPU keeps on executing one of the process, and the others they continue. If there is a DMA support, they can continue with the IO operations. So once they finish, once they complete, they will interrupt the CPU as we found, and the interrupt processing hardware will say that okay, it is done. And if it change the status of that process, which was doing IO, into the running, into the ready state kind of, so that now that process can join or can request the CPU because its IO is done. So so this is important. The DMA operation is important because through this we can achieve high data rate transfers as well as concurrent operations of IO and CPU. So all the modern ways it supports or it utilizes the DMA facility, and all the modern computing systems also do support DMA. But this programmed IO and interrupt driven IO were used in some time back, and these are no longer in use. Okay. So now we focus on the evolution of operating system. So we talked about in brief about the general components of a computing system, and we'll see that with how this computing system evolved or the computational environment evolved, as well as the different features of CPU also evolved. So here is a list of different class of operating systems, right from late 50s or early 60s to so it's noted as 1990s, but again there is not too significant change in the philosophy, rather than you are having OS these days. So you should have written like a modern OS. So the modern OS includes, say, operating system which is written for smartphones, maybe smartwatches, or maybe small devices. So that is how it is getting changed. But the majority of the operating system concepts evolved since 1960s to 1990s, and these days you are getting a network of uh, I mean different systems connected to internet or network, or you are having a view that you are having sitting in a large virtual machine, the concept of distributed systems, or maybe there are real-time systems. So we'll talk about those, but we'll see that the most of the concepts that we'll be referring in this course, and which are the most fundamental concepts related to operating system, are focused in these 3 operating systems. So majority of the concepts evolved during those time, and this multi-programming and time shared systems will have most of them. So you'll see that what they are and how do they change, and how the design of the OS become more and more complex with time. Okay, and while talking about this evolution, we'll also see how the computational requirement also changed. Or in other words, sometimes so program is something like a set of functions or modules, but job is a sequence of programs. So it is something like when we run a code, we have to first compile it, link it, and then execute it. So if I want to execute my C program, I have to first compile, then link with some math libraries and all, and then I have to actually execute. So we can think, we can consider that these three uh, programs, the compiler program, linker program, and the actual executable program, these together will be executed in some sequence, and this sequence is very important. You cannot execute before you link or compile. Okay, so the notion of job is a sequence of programs that together achieves a common goal. Okay, so when we talk about think of a job means we consider that there is a sequence of programs which are run one after the other. Process, as we already found, that this is a program in execution. So when the program gets executed, we call it as a process. And the sub request is the presentation of a computational requirement by the user to a process. To be specific, say when I'm running a matrix multiplication. So what I do, I first display something that enter the values, 3x3 or 4x3 matrix, 4x4 matrix. So prompt comes, and then I input the values, and then in my program I may expect that whatever I have entered, it should display to make sure that, so that I can make sure that it has read it properly. Okay, so here this when I type on the values, I press enter, I would expect the system should store those values in the array which stores the matrix, and it should display it back. Okay, so after the last key press, I submit a request, implicit request. It's a kind of sub request, you can say, which is to display the contents back in my monitor. Now once it is done, again then I say that, then it says that okay, give the options. First one is for multiply, 2 is for add, 3 is for subtraction, like that. I give 2, so 2 means it will go for addition, and it will display the result. Again the menu comes, it says that okay, enter your choice. I give say 1, it goes for multiplication and gives a result. So generally in a typical interactive environment, interactive means where we are having a keyboard, we are having a monitor, and the CPU, we are having a dedicated CPU if it is a desktop, or we may not have a dedicated CPU if it is a server based system, but we'll definitely have a desktop and a monitor and a keyboard. So in such an interactive environment, the user is interested in submitting small sub requests, and it would expect a very fast response from the user, from the computer. So the program is a matrix multiplication program, but while the program is running, it is interacting with the user multiple times, and every time the user enters the input, whatsoever, it expects the response from the system in terms of some display. So sometimes a program is composed of several sub requests, and in a typical interactive scenario, computing scenario, such things happen. Okay, so we'll see that as the operating system or the different hardware evolves with time, how the computational requirement to a system changes, and accordingly the design of OS also becomes more and more non-trivial. So let's start with the batch processing OS, which was written in early 60s, or you can think of the late 50s, and this is the case. So batch processing OS 1960s, and it was first developed. The first batch processing OS was developed by General Motors in mid 1950s for IBM 701 machine. And if you can see this image of IBM 701, so this is one particular machine. I mean, this almost encompasses a big room. I mean, you can think of a big lab. So it has got several components. This is the input output and all this. This is a system, and there is a huge cooling arrangement that's required the system to run. Okay, so that was the situation, and the most important thing is these machines are so costly and they need to be maintained in a very protected environment. And even those days there were no concept of interaction, direct interaction with the system. So if I am a computer programmer, I am a scientist or a mathematician uh, those days. So if I would like to run some program, I cannot directly sit in a terminal and type on in the keyboard. So there was no such concept. There is no concept of keyboard terminal like that, which is accessible by the end users. Rather, the users used to feed their program, or submit their program in form of some punched cards. These are the views of the punched cards, which these are the punched values, and this is a kind of machine which where you can, if you type some instructions, it will be punched in a card, and these cards you have to handle to the operator. So there will be operator, one or two operators which will be operating this machine. And if you have written some program, you have to use this particular system which will generate the cards where the program is coded. And these cards, if you present, it will feed these cards into the card reader, and that card reader will then read your program and will feed it into the program memory, and it will be executed. Again, the output, whatever it is. So if you are generating, if you are multiplying to matrix, say for example, so there's a card to write that you have to multiply matrix. Those days there were Fortran language. So in Fortran you write, you provide the data, and the output of the multiplied matrices will be again written in form of a card, and you can get it decoded to know what was the values and if it is correct or not. Okay, so it was basically a tedious job, and it is much more complicated. Like running a code, it might happen that you submit a job in today early morning, like many others. So everybody used to kind of assemble in the computer center to submit their jobs. And there's an operator who used to collect all the jobs and form batches. So that's why the term batch comes. So a set of jobs. So first of all, a job is a collection of programs. Each program is consisting of a set of job cards. Okay, these punched cards. So several such programs forms a job, and several such jobs forms a batch. Okay, so a batch of jobs is actually formed by the operator, by the computer operator manually. Okay, so most of the tasks that we these days the operating system used to do, those days were mostly done manually. So the operating system, the code is pretty trivial to write. Okay, the focus was how to get the computations done in a machine rather than having a very user-friendly interface of the system, because uh, it was all operated by a specially trained computer operator. Okay, and maybe you are expecting, you would expect a outcome of your program or the result the next day evening. Okay, so that depends what the policies are. So, and it can be scientific computation or number crunching operations like that. Now the prime concern here is to minimize the CPU idle time, and the functioning is, so in this case there was no concept of multi-programming. Okay, so we are talking about simple batch processing. So here what happens, the basic idea is uh, execute one job at a time, and within one job one program at a time, and that is very critical. I mean, that is very important. So the notion that multiple processes or multiple program codes will be simultaneously existing in the RAM never exists in those primitive ways, primitive systems. So a single user process is here, and so it shares some space with the batch OS kernel, which is better known as monitor. And the basic idea was, so one by one, so in a batch, in a particular job in a batch, in a particular program within a job within a batch, it is loaded. Okay, so when it is loaded till it gets completed, the next program of the job cannot be loaded. So that's a kind of problem. And that was the best thing that people would have expected. Okay, now the computer operator forms the batch as a sequence of user jobs, and there are some special cards which used to plug in as special marker cards which differentiates two jobs. At the same time, the operator had to intervene only at the start and end of a batch. So that's why he used to form batches. So he can form a batch which he expects to run for maybe 2-3 hours, and a batch contains say 3-4 uh, say jobs. Okay, so after 2-3 hours he again forms a batch and then loads it if the previous one is done, like that. So the operator need to intervene in between the start and end of a batch, and these are the basic things. So basic computational unit is a job. The the operator forms a batch like this, and the basic objective is to minimize the CPU idle time. Now the concern is how to minimize the CPU time. Before we do that, so this is the kind of how the program would have looked like. So execute Fortran uh, compiler, then execute the compiled code with the data and all this. Okay, so you could have called the linker also like that. So each of these instructions that we can see need to be punched in a punch card, and there can be multiple such cards which actually is having the code. So the key idea is automatic transition between jobs. So these special cards or these punch cards with some special commands facilitate the automatic transition between jobs, because the operator never intervened in between jobs, because within the batch it wants the machine to take one by one the jobs of a batch and execute it and go to the next job, like that. So automatic transition of jobs is important, and because of that, special control statements and command interpreter is required. So whenever the card containing the control statement is read, the monitor here interprets that and accordingly it takes action. Now to speed up the process or to reduce the CPU idle time, what happens? Say this is a CPU. So this is a CPU, and this is a card reader, and this is a line printer. Say I want my output to be printed, and I'll be taking out that taking away that one. So you see, CPU is relatively a faster processing unit compared to the card reader or the line printer. Now the point is, if one process is loaded in the memory, computer memory at a time, one program is loaded. So once that is done, the printing is going on. Now when the printing is going on, the CPU remains idle, because the printing might take a few minutes. Okay. Now once it is done, now the CPU says the entire process is complete. Now the CPU will interrupt or I mean it will seek from the card reader the next program. So the next program will be loaded from the card reader to the disk, and from the disk to the RAM, and the CPU executes. Okay, but when it reads from the card reader, during that time the CPU remains idle. Again, after processing, when the output getting printed, then also the CPU remains idle. So CPU idle time, the prime concern is how to minimize the CPU idle time, how to maximize the CPU utilization is one major challenge. And to enable that, there was a solution which is called spooling, simultaneous peripheral operations online. What it did, there is another processing unit here and the processing unit here. So the thing is, when the CPU was executing, say, the fifth process, which is currently in the disk and is loaded in the RAM, during that time, probably the CPU is printing the output of the fourth process in the line printer. I mean, not the CPU, but there's some low-end processing unit which takes care of uh, displaying the or providing the output in the printer corresponding to the fourth process. At the same time, here simultaneously the code of the sixth process is or program is getting loaded from the card reader to the disk. So the idea is, if we have some low-end processing units here, which is not as powerful as a CPU, while the processing is going on for the ith process, the I plus 1th process can be loaded from the card to the disk, which is time consuming. At the same time, the I minus 1th process output can be printed in the line printer. And this simultaneous peripheral operations online, this is better known as spool or spooling. Okay. So this is in some systems this is incorporated, this is deployed to speed up the uh, processing or to increase the CPU idle time, so that CPU don't have to wait or for a long in between two jobs now. Okay, so in such a system, what can be the performance metric? So the performance metric is, so you know that I have submitted today morning and I would be expecting my output in tomorrow evening. So if the system operator says that okay, you can come today evening, then I'll be happy. So from the user's perspective, the performance metric is the turnaround time. What is the turnaround time? The time from submission of a job or program or process by a user to the time its results become available to the user. So if the job is submitted in this morning time, so the batch at say 8 a.m. the batch has been formed probably at 9 p.m. and then the execution of the batch continues here. Maybe it takes in the evening today, and maybe the result printing goes up to say another 2 hours, okay, in the late evening, and then only you can come and collect the results. So the thing is, the turnaround time is from here to here, but you can see that your program is just, you have written a very small code of just multiplying two 4x4 matrices in Fortran just to see that whether you can understand the code and all this. But you have to wait for the whole day or maybe more than a day to get your work done. So the performance metric, you don't actually care about how fast the CPU is working or not, but you know that the turnaround time is really too much. Okay, so those are the type of OS. The most primitive OS, that is the batch processing. It was developed in late 50s or early 60s, and the prime concern was CPU idle time. The performance metric is turnaround time. Sorry, it's mistaken. So this is not. So it's a turnaround time. And the key concepts was automatic job transitions, pooling, command interpreter, monitor, real memory organization. Why real memory? Because the entire process need to be stored in the primary memory, and there is no concept of virtualization. So it is all simple, and even no two process simultaneously occupies the user partition. Okay, so everything is very simple, but still even after going for spooling and all, it was found in many cases that the CPU utilization is often as low as 4 to 5 say 4 to 5%. So most of the time is basically wasted in reading and reading from the disk or loading things from the card reader and all this. But anyway, this was the first of its kind operating system that prevailed. So a modification of that will be the batch multiprogramming. Okay, so it was earlier it was a batch OS, pure batch, and this is batch multiprogramming. So this is a key term, and it evolved in the late 60s. Okay, so people found the problem that there is a huge wastage of CPU time. So how to utilize it? So then they thought of that let the basic computation unit be still job, so it's still the same, and the environment is still non-interactive. So still you cannot think of any kind of keyboards or monitors. The users need to interact or get things done from the system via the computer operator. So user submits jobs to the operator, and it forms a batch. But these batches, when they are getting executed, the key the concept that the new concept that came is that it's a concept of multi-programming, where multiple user programs now can coexist in the RAM. Okay, it's something like this. So it's a multi-programming kernel or the monitor, and here you can see program 1, program 2, program 3. All three coincides in the RAM. Earlier it was just one, a single process here. Okay, so this is the basic change, and it not only changed the way things work, and it also came up with new challenges in terms of the operating system design, but also it has come up with different advantages also. So here, why we did that, why that concept was involved, was introduced to minimize both CPU and IO idle time. Okay, so here the kind of The objective is the maximize the resource utilization. Resource means both the CPU resource and the IO resources. We would like to maximize. So how to maximize it? If the CPU remains busy with one processor, if there are some other processes also loaded in the RAM, so those processes, if they want, they can just go on and use the IO. And whenever the CPU, this current process relieves the CPU, some other process which is waiting, which has completed IO, it can take on the CPU like that. So neither the CPU remains idle for long, nor the IO devices remains idle for long. If we can accommodate many such processes in the system memory, in the RAM. So as you can see, those days there was just one physical processor in the system. So although there are three programs or processes, so here you see this is the running program at some point of time, and this program is doing the IO. At some later point of time, maybe the third program is running running the CPU, and the other two are busy in IO. And in some other point of time, maybe program 1 is getting executed by the CPU, and this program 2 is doing IO, and program 3 is just waiting for the CPU maybe. That's why it is not doing anything. Okay, so they actually will compete in such a fashion that we expect both the resources CPU and IO will be utilized to the maximum. Okay, but in doing so, there are new challenges that occur. Before we get into those challenges, let us see the timing diagram. As you can see here, program 1 and 2, it might happen that, say, at a particular point of time, say this, when this program is doing the CPU, is executing the CPU, no other program, so the program 2 is not executing CPU. Here, CPU is is executing, say, the program 2, and program 1 is doing IO. Okay, here this is doing CPU, and here this is, so it's like in an alternating fashion. They are using the IO, they are using the CPU, and if there is one process, we could not have taken the benefit. So if the process is busy in IO, the CPU simply remains idle. So what are the key concepts or features in the batch multiprogramming OS? So the first thing is, we are expecting that the CPU will be busy in executing some process while some other process is doing the IO. And this can only be achieved if the system supports, the hardware supports DMA. Just now we explained that. Okay. We expect the DMA support is there, and only then this batch multiprogramming can be implemented. Memory protection, we talked about it earlier, that if multiple processes coexist, there must be some bound registers, or you can think of a base register with some size, which will provide us the range of the locations that a particular running process can access in the user mode. Okay, and this is extremely important to protect other user processes and the kernel modules from getting corrupted. Now the kernel and user mode of CPU, this is also important, because whenever the user process is willing to access some other resources, it will make a request via the kernel. So it will get into the kernel mode and it will do so. So the kernel mode and the user mode, those concepts start coming. And then there is a concept called CPU bound program and IO bound program, and we'll see that how these are useful. So we say that multiple programs can coexist, or they can be loaded in the system. So a CPU bound program is something like which uses most of the time it will be busy in using CPU. So the CPU time that it requires is most. So once it gets the CPU, it executes the CPU, or it holds the CPU for, say, maybe several minutes. Okay, but a CPU bound program, if it requires some IO, so CPU bursts are long, and if it requires IO, it will be requiring IO for a very small amount of time, maybe few milliseconds. Okay, whereas in an IO bound program, if IO bound program requires a CPU, it will require the CPU only for a very small time instant, maybe just a few seconds. Okay, and if it and then it goes for IO. So a IO bound program is more of doing CPU IO like that for small bursts, and a CPU bound program will be doing will be utilizing CPU or using CPU for long bursts and IO for very small bursts like that. Okay, so if you think of the CPU bound jobs will be something like this. So yellow portions are the CPU usage, and the white portions are, say for example, the IO usage. It's something like this. But in an IO bound job, it will be something like this: CPU, IO, CPU, IO, like this. So the CPU bursts are very small. So these are IO bound. Okay. So this is a IO bound program. This is how the pattern of CPU execution will look like. This is a CPU bound job. That will how this look like. And these yellow portions denote CPU execution time. Okay. Now here, when you have got multiple processes competing for the CPU, because you have already accommodated them, and it might happen that uh, more than one of them is ready for getting the CPU. So they are not waiting for the IO. They are ready for CPU to be allocated to them. And if they are allocated the CPU, they know that they can continue with the CPU execution. So now in that case, if there are multiple such processes which are waiting for the CPU, so which one should you prefer? Okay, so this is a policy matter, and you have to how to decide whom to allocate. To do that, there's a concept of priority. Okay, so programs are now given some priorities. So what is a priority? It's a non-zero integer value. Maybe higher the value, higher the priority, something like that, or maybe it's the reverse. So a priority value is assigned to a program. Now, when you have got a mix of programs, some of them are IO bound, some of them are CPU bound. So what will be the policy? What will be the policy so that both the utilization of CPU and IO is maximized? Can you think of it? So there are only two possible options. One is you give more priority to the CPU bound processes, or you give more priority to the IO bound processes. Okay, and which one should we prefer? See, if we give more priority to the CPU bound process, so what it will do? There is a CPU bound process, it gets allocated, so it will continue using the CPU for a long time, and by the time it may happen that 3 or 4 IO bound processes, they are ready for running in the CPU. They have completed their IO, but they cannot use the CPU, and neither they can use the IO also, because they say that we have just now completed IO, we are waiting for the CPU, and if you give us the CPU, I'll just use for a small amount of piece of time, but without that time I cannot go and get the uh, make the IO also busy. So that's a problem. And if you give in such a case the priority to a CPU bound job, so the whole utilization is like CPU utilization is good, but the IO utilization will fail. It will drastically fall. But if we give more priority to a IO bound job, what have happened that, like, even if the CPU bound job has been allocated the CPU and it is running fine, but at this point of time, if it finds that there are some IO bound jobs which are ready, there are some IO bound jobs which are ready to get the CPU, then the operating system makes a policy that even though it was running, it will forcefully take out the CPU from that process. Okay, this is called preemption. We talk about this term. So it will forcefully take out that process, and it will allow one of these IO bound process to get the CPU. Why? Because it knows that once it uses a CPU, it will just use it for a very small amount of time and release it. So once it releases it, that process will go on and keep the IO busy, and then maybe some other like this. So overall, the policy is to allocate or the CPU, or to give preference to IO bound processes more and more compared to the CPU bound processes. So that's why the policy is an IO bound program or process should have a higher priority than a CPU bound program. Okay, so what is the CPU scheduling? What is the term we use for this? So there are different types of scheduling. Scheduling means which of the processes will get the CPU. What is the policy for scheduling a process, a ready process to be allocated to a CPU. So here we call this as priority-based preemptive scheduling. So the term can be, it is self-explanatory because we know what preemptive means, what priority means, and a low priority program executing on the CPU is preempted. Low priority means a CPU bound job. If it is executed in the CPU, it will be immediately preempted if a higher priority program, that is IO bound job, is ready for running. Just it has returned from IO, so it will be forcefully preempted. So it's a kind of preemptive priority based scheduling. So another key concern in the system design is degree of multiprogramming. What is that? So the policy is that, or the basic functioning is that the OS designer decided to allocate, load multiple programs or processes simultaneously. But then people will say that how many do you allow? How many do you load at a time? If you say that I would like to load say 1,000 programs, what will be the problem? The simple problem is because RAM is finite and you have to accommodate every process or program at least some small portion of RAM. And if it is real memory uh, multiprogramming, there is no concept of virtual memory. So the program size is the size of the programs, the maximum size of the programs that can run in a system is very much limited. Okay, so this is a basic problem because you basically partition the user space in very small size. Okay, but so you cannot probably introduce too many programs or processes at a time. So the value of the degree of multiprogramming should not be too high. Okay, at the same time, if you think of having a very low value of multiprogramming, so you just allocate two or load you set the limit to 2 or 3. That means you can load at most 2 or 3 processes at a time. Then the problem is now you are not having sufficient programs to keep the CPU and IO busy. The previous problem triggers. So it is often tricky to find out what should be the best value of degree of multiprogramming. Degree of multiprogramming is the number of programs that the OS keeps in memory all the times. Okay, so we can typically guess this kind of plot if we increase the degree of multiprogramming. If the degree of multiprogramming is very small, then the utilization will be less. If it is more, utilization will be more and like this. So here we plot throughput. So I'm coming to this point. So these are the different key concepts and features related to batch multiprogramming systems. And the performance metric earlier, what was the performance metric? It was the turnaround time. So the turnaround time means again the same thing. Now the user is not interacting directly; it's a non-interactive scenario. So the user simply submits the job in the early morning, and instead of the next day evening, now it manages it better. So maybe the operator asks that what kind of job you are having. So it says that okay, it's a IO bound job, or it's not a big job. So the thing is because there are multiple programs got loaded. So it says that if it is so you can just inquire today in the afternoon or evening. Might be that yours will be over. And somebody who is submitting a CPU bound job, the operator says that no, we don't give too much priority to your jobs, so you probably come after 2 days. Okay, so something like that. So the thing is the turnaround time, you see, if you consider turnaround time to the performance metric, that now might vary. Okay, because the IO bound jobs will will probably experience a lower turnaround time, maybe because maybe they're requiring 5 IO operations and very few CPU time, and that will be over. But a CPU bound jobs will have a higher turnaround time. So this is from the user's perspective, but we can have another performance measure which is more relevant from the system's perspective. So now, after doing so much of changes, what the system designer feels, the system designer says that the operator says that this system, uh, why should I bother about turnaround time? Because now I find that the system can process say maybe 15, it can complete uh, jobs submitted by 15 users every day. Okay, or maybe 20 users every day. However, he agrees that okay, there are maybe few users who need to wait for 3-4 days. But again, from the system's perspective, the throughput will be very high, and the system designer will be happy, because sometimes those days you have to pay for your computation getting done, so they will be earning more, because and they shows that there are so many jobs that got completed. Okay, so apart from turnaround time, this throughput also became a important performance metric, which is from the system's perspective. It's a ratio of the number of programs processed and the total time taken to process the time, this ratio, or in simple terms, you can say the number of processes completed per unit time. Okay, so the degree of multi-programming, if you have got very less number of programs or processes, the throughput definitely will be very low, because you are offering less load. If you increase the degree of multi-programming, you can expect that they will be utilizing both the CPU and IO to the maximum, and the throughput of the system will increase because of the IO bound jobs getting completed very fast. But at some point of time, you know that there are too much of switching and all this, and it will take some time. So throughput cannot be beyond a certain level. So you cannot expect that 1,000 processes gets completed per day. That is not possible. Okay, so there is always a saturation value of the throughput. Okay, so uh, that's a kind of operating system which is a modified version of batch processing. It's called batch multiprogramming. It was in late 60s. The prime concern was resource utilization. Resource here means both CPU and IO, and there are several features or concepts got introduced: multiprogramming, DMA, memory protection, user and kernel mode, IO bound, CPU bound programs, priority based preemptive scheduling, and degree of multiprogramming. Okay, and the performance metric, earlier it was only turnaround time, and now we can consider the throughput also. But these two are, sometimes conflicting, because one is users and one is from the system's perspective. Now, what this particular OS lacks, so I think let me complete this part. So there are only 3 slides. I'll take another 10 minutes of time. If you don't have any other classes now, may I continue for another 10 minutes? Hello? Hello?
Sir, we don't have any.
Yes, sir.
May I continue for another 10 minutes?
Yes, sir, sure.
No, sir.
Can you hear me?
Yes, sir.
Okay, I don't know. Let me continue. So it's a batch multiprogramming. The basic drawback was it was not suitable for interactive environments. Okay, so interactive environment means where the users can interact. So because where users can interact, uh, the operating system was not designed for that purpose. So let's see what happens when user can interact. So we've got a different type of OS which is called time shared multiprogramming, and it evolved in early 1970s. Okay, and the first time shared OS was written as a part of MIT project MAC, in the MAC group, and they developed a OS called CTSS for IBM 709 during 1961. So in the late 60s again. In 70s, a lot of time share multiprogramming operating systems came in existence. So here the basic difference is the basic computational unit is no longer a job. It's a sub request. And we have already talked about sub request. What sub request means. The environment is no longer, it is now modified, it is interactive. Okay, and you can see the from this image that now the users, they are having keyboards and they are having monitors. Okay, so every user is having a keyboard and the monitor, and they can interact. And probably they are not having a CPU of their own, because the CPU is a kind of server which is in some different machine, different room, but they all can interact with that CPU through their terminal as well as monitor. And sometimes such terminals are called dumb terminals, because the user is only equipped with the terminal but no computational resource. Okay, So here the user submits a sub request using keyboard and examines its response in the monitor screen. So what it means, as we mentioned, so I just give a prompt, I give enter a value, and I would expect the display to come. Again, I give a choice of menu. Once I press it, it will get the addition done. It will show me the result. Again, it shows the menu. I give another choice. It shows. So the thing is, during the whole execution of a program, so just one program is running, matrix multiplication. It's a menu-based program, say for example. So when it is running, the user is interacting with the system directly, and the entire execution of the process is or can be considered to be a sequence of multiple sub requests that the user makes to the computing system. Okay, so here the primary concern, so it is not, so the complete scenario got changed. So here the user is not going to an operator and submitting a job and he's punching it and he's forming batches. It's no longer like that. The user just, he has got a terminal, he has got a login or a password authentication. He's an authentic user, and if he logs in the system through the terminal and keyboard, he gets a shell or some kind of interface through which he can trigger his programs, his processes, and he can write an interactive program. Okay, so like that. So the prime concern here is minimize the response time. So we are no longer interested in the turnaround time. So here the turnaround time becomes, the measure of turnaround time becomes completely vague, because it may happen, I mean, in fact, in those days, it used to happen that a particular scientist or a mathematician, he goes to the computer room and he grabs a terminal and he starts working from 8 a.m. and he continues up to say 3 p.m. Okay, so during this whole 4-5 hours he executes multiple programs. Each program has got multiple sub requests like that. So his turnaround time is not, he will not bother about waiting for so long. So his turnaround time is not say from 8 p.m. to 8 a.m. to 3 p.m. It's irrelevant now. Rather, he will be more interested in finding out that how much time the computer takes to respond whenever he submits a request, a computational request. And in such a system, as you can guess, that in the early morning when there are very few users, because it's a kind of server kind of machine which is being shared by all these users. So in the early morning, if there are 10 users, probably they will get very fast response to their request. So almost immediately, within a second, they will get the request, or millisecond. But as the day grows, I mean, as it becomes afternoon, I mean, evening and all this, in the midday, there will be more and more users. So once there are 100 users, so the CPU or the processor need to cater to all those 100 users, and now the problem is it becomes overloaded with programs or processes. So it might happen that the user who got very fast response in the early morning is not having sufficiently fast response in the midday, in the noon, or in the evening. So the prime concern is always how to minimize the response time irrespective of the load, and which is really challenging. Okay, so here we are not interested in minimizing the turnaround time, neither we are interested in minimizing the throughput, because user is interacting. Okay, but the user is mainly bothered about minimizing the response time. Each and every time he submits a request, he wants a very fast response. Okay, no matter what the load in the system is. So here, how the functioning, how that can be ensured, the minimizing response time. Now you see the computationally, earlier what the CPU did, the CPU, if there was a CPU bound process, it continued using the CPU for say for example for 5 minutes or 10 minutes. If there is a IO bound process comes, it will preempt the CPU bound process and it will get hold of the CPU. Once it is done, then the scheduler will find that if there are some more IO bound process, it will be scheduling it, it will be allocated to the CPU like that. But here in this case, it will not be like this. Say the idea is no process will be able to utilize the CPU for a longer period of time, no matter what type of process it is. So even if for IO bound or CPU bound process, there is a small time slice that is defined, and any process which is utilizing, which got the CPU uh, allocated, will be utilizing the CPU for that small time quantum that is defined. And the small time quantum is sometimes 1 millisecond or few milliseconds only. Okay, so that's the idea, because users are more and more interactive. So CPU bound processes are very few. Users are more interactive users, and to accommodate them, there is no point of having that kind of priority based scheduling. Okay, so sharing the CPU time among processes in such a way that each process to which a sub request has been made to get a turn on CPU without much delay. So that was the basic objective. So what are the key concepts? The key concept is time slice. So time slice is the largest amount of CPU time any time shared process can consume when scheduled to execute the CPU. And what is this largest amount? This is typically just few milliseconds or nanoseconds. Okay, or nanoseconds. So no matter what type of process you are, no matter what how much requirement you have got, no matter how many other processes are waiting or not, a process which got the CPU, it need to release the CPU after the time slice of few milliseconds. Now, if it happens that no other processes are at that time ready, the same process can be rescheduled, but you have to release the CPU after that time slice. And to implement that concept or idea, the concept of timer interrupt came. What is a timer interrupt? Now, every time the time slice elapses, there is a timer interrupt, and the timer interrupt will interrupt the CPU. It says that you should no longer execute the current process. You should stop. Okay. So this timer interrupt is interrupt which is triggered uh, based on the clock ticks or clock ticks, and whenever the clock ticks or that timer after getting reduced every time, after every tick becomes 0, it triggers the timer interrupt. Okay, so the timer interrupt gets triggered every milliseconds or nanoseconds as a time slice. And what kind of CPU scheduling will be there? Now, the CPU scheduling need not be priority based, because there is no priorities as such. This trick of applying a small time slice will take care of it, as you can guess, because if it is say, if there are, these are the number of processes, so some of them may be IO bound, maybe CPU bound, we don't care, but the thing is they forms a queue. So all the processes which are ready now forms a queue. It's called a scheduling queue, and this is a scheduler algorithm. Okay, so the scheduler algorithm will select one process from this, so it will execute round robin scheduling. What is that? Is a it's a circular queue kind of thing. So this process gets scheduled here. After the time slice, this process, if it is not requiring the IO, it will join at the rear of the queue, and the next, the process which is in the front of the queue will be scheduled. If this also is not requiring IO, after the time slice, it will join to the rear of the queue, like that. Now the next process comes. That process, even before the time slice elapses, it might require an IO. Okay, so the time slice is 1 millisecond, but before half of a millisecond, after half of a millisecond, this process requests IO. So what will happen? There is no longer use of CPU required. So sub request is completed or IO operation is started. So in that can be one way of releasing the CPU. So once the IO is done, it will again join the end of the queue, like that. So as you can see that there is no explicit priority, but here automatically IO bound job will get the CPU, it will do the CPU operations, and it will then go for IO, join back, get its turn, do the CPU, get its go for IO and come back, like that. And after a few such rounds it will complete and it will say that it is done. But a CPU bound job, it will get the CPU, there will be a timer interrupt, again it will join, and in a long queue it will come, again there will be a timer interrupt because it is not releasing it, it will be forcefully preempted because of timer interrupt, it will join the rear of the queue, again it will come, again it will come. So a CPU bound job may require, say, maybe several thousands of times it will require the CPU to get its work done because it never cares for IO, and definitely it will take some long time to get completed. And because it's CPU bound, the user is also not waiting for the response, maybe something like that. So it's not hampering the response time, it's not affecting response time. Rather, the IO bound jobs, which are actually affecting the response time, they are getting completed, or they are getting their turns in regular intervals. Okay, so that's a beauty of this scheduling algorithm. It's a round robin scheduling, and there are several variants of this which we'll discuss while talking about uh, process management in details, and what kind of variants of this are used in Linux based operating systems, that also we'll see. Okay, so this is one interesting implementation of scheduling in the time shared multiprogramming. So you don't have to think of priorities, and things will be taken care of automatically. And another important feature is virtual memory organization. So because of now the users are sitting and interacting, and you can have, you don't know how many users will be logged into the system, because they are all once they are logged in, now they want their codes to be executed. So in that case, if you allow a particular user to load its entire program, it will eat up a lot of RAM space. So the idea is you create partition, and each user is given some portion of the RAM to get its code executed. But at the same time, the virtualization of memory helps the user to run bigger codes even in that small portion given to them. Okay, so this can be done in a very smooth fashion. So this is the example of the kind of operating systems that we still use these days in our desktop, the desktop operating systems, and even the server-based operating systems. So while talking about process management, we'll be mainly focusing on or having in our mind this time shared multiprogramming OS. So try to recall the computational unit, the environment, prime concern, and all this, because most of our discussions will be based on this. And the performance metric that will be important here is probably not the turnaround time, not the throughput, but the response time. And the response time is the time from submission of a sub request by a user to the time a process responds to it. So it is, you see, the response time is similar to the turnaround time, but the only difference is this: the time from the submission of a job, instead of job, it is a sub request. It's a portion of a job or a program. Okay. So here the main point is the user is not concerned about how long its entire process requires to get completed. It is happy if the system interacts or responds very fast to its submissions. And this is the response time, and this is the efficiency. This is also important. Uh, so these are the performance metrics. And the time shared multiprogramming, the performance metric is the response time. The prime objective is a good response time. The different concepts involve time slice, timer interrupts, round robin scheduling, virtual memory organization. So the only drawback that it has got is the response time depends on the system load, and you don't have a predictable response time, and which is essential in some specific type of systems, and that is real-time systems that we'll talk in the next lecture. Okay, so the real-time operating system requires a predictable response time, and it cannot and it's a kind of guaranteed response time, which a time shared system cannot guarantee. And while working in the server, you can feel the difference of the response time when there is a high load or low load condition. Okay, so that's the end of today's lecture. So if you have got any queries, you can ask me, or you can write